This lecture is going to cover sections 3.1, 3.2, and 3.3 in your textbook, and it's going to be covering the topic of search as a mechanism for problem solving in AI. So to begin, today's lecture is about reframing how we think about problem solving in AI. By the end of this class, I want you to be comfortable thinking of problems as graphs rather than formulas, and solutions as paths rather than outputs. That shift matters because because many real AI systems are not computing answers directly. They are exploring possibilities under constraints. And then we're going to talk even more about constraints next week. Everything we do today, from state space modeling to search strategies, is building toward this way of thinking. In many AI problems, you're not handed a clean algorithm that says, do these steps and you're done. Instead, you're given a specification of what counts as a solution, and you have to find one. And that's what search is. The agent is in some state, it has actions it can take, and it wants to reach a goal state. Once you abstract away the domain details, a huge number of AI problems reduce to finding paths through a graph. The important point here is that there is often more than one way to represent the same problem as a graph, and those modeling choices matter. So this slide is here to reset your intuition. In cybersecurity, we're almost never just diagnosing something in a single step. Incident response, threat hunting, and attack path analysis all involve navigating uncertainty. When an analyst pivots in a SIEM, runs an EDR query, or traverses an IAM graph, they're not confirming a single fact, they're moving through a space of possibilities. And that is a form of search. And cybersecurity work is full of decisions about where to look next, what to ignore, and when to stop, which makes search a natural mental model for the domain of cybersecurity. Now, this slide gives you a vocabulary for describing different kinds of search problems. Some problems have flat state spaces, others are hierarchical. Some are fully observable, others are only partially observable. Some have deterministic dynamics, others don't. The point is not to memorize these categories, but to recognize that search problems differ along multiple dimensions. When a search strategy works well in one setting, but fails badly in another, it's often because these underlying properties of the problem that it's trying to address are different. And formally, a state space problem has a set of states, some start states, a set of actions, and a way to move from one state to another. It also has a way to recognize goal states and a criterion for what counts as an acceptable solution. That last part is important. Sometimes any solution is fine, and sometimes we care deeply about optimality. Once a problem is expressed in this form, we can reason about it independently of the original domain. That abstraction is what allows the same search algorithms to be reused across very different problems. And this slide on cybersecurity problems as search problems draws a line between the formal definition you just saw and the cyber domain that you care about, since that's what you're studying here. Many cybersecurity tasks are not prediction problems where a model outputs a label. Instead, they're search problems where analysts explore paths, explanations, or sequences of actions. And so attack path discovery, incident investigation, vulnerability chaining, and response planning all fit this pattern. Framing them as search problems helps us reason about complexity, trade-offs, and failure modes in a principled way rather than treating each task as ad hoc. Now, this example here looks simple, but it's doing important work for us. This is an example problem for a delivery robot, and the robot is in a specific location. It has a limited set of actions, and it's trying to reach a goal. So here, the goal is stated. The robot is at A, and the goal is to get to G. What matters is not the robot itself, but the structure of the problem. There are discrete states, allowable moves, and constraints imposed by the environment. And so in this kind of example is the first place that students often realize that problem solving in AI is not about clever formulas, but about how you describe the space that the agent is allowed to move through. And now let's talk about the delivery robot as an attacker, an analogy in the cybersecurity domain. So here's where we intentionally reinterpret the example to fit the domain of cybersecurity. So the robot's environment can be read as corresponding to an enterprise network. Nodes correspond to hosts, identities, or cloud resources on that enterprise network. Edges correspond to authentication paths, trust relationships, or misconfigurations. And obstacles are analogous to defensive controls. So when the robot reaches the goal, that is not success in a neutral sense. It is privilege escalation or data access in the cybersecurity analogy. So the point is that attack behavior is not mysterious. It is structured movement through a constrained space. And that's how search applies to the cybersecurity domain and problems that you're trying to solve in cybersecurity. Now, this slide formalizes what we've been intuitively using. A directed graph gives us nodes, arcs, and paths, which is enough structure to talk about reachability and cost. In cybersecurity, directed graphs show up everywhere, even when we don't call them that. Network flows, IAM relationships, dependency chains, and trust boundaries. Once we model a problem as a directed graph, questions about security become questions about which paths exist, which paths are cheap, and which paths we failed to anticipate. And now, this slide on mapping search concepts to cybersecurity makes explicit something that practitioners already do implicitly. When analysts think about where an attacker could go next, they are reasoning about transitions. When they talk about blast radius or impact, they are reasoning about cost. Different modeling choices produce very different graphs, which is why two tools analyzing the same environment can reach different conclusions. This is not a bug. It reflects the fact that modeling is an analytical choice, not a discovery of objective truth. So next we talk about what is a state. And this slide is deceptively important. A state has to contain enough information to determine what can happen next, whether the goal has been achieved, and what the cost might be. In practice, this forces trade-offs. If the state is too simple, you miss real attack paths. If it is too detailed, the search space becomes unmanageable. The phrase, as simple as possible but no simpler, is doing the real work here, especially in complex domains like cybersecurity. So keep the states as simple as possible, but no simpler. So now we'll look at what is a state in a cybersecurity context. In cybersecurity, a state might include credentials, access level, network reachability, active sessions, or configuration settings, but it rarely includes everything that might matter. Temporary tokens, cached permissions, timing effects, and implicit trust relationships are often excluded. This slide is meant to make you uncomfortable in a productive way. Every model hides something, and search can only operate on what the model represents. Understanding what you left out is as important as understanding what you included. And then, as you build your model, striving to find the best balance between the two, between what you explicitly include and what you choose to leave out. So now we're returning back to the slide that we already looked at before, the example problem for the delivery robot, where the robot is at A and the goal is to get to G. So again, this is the first example in today's lecture of a concrete state space problem, and it's intentionally simple. The robot starts at a specific location and the goal is to reach another location. The robot has a limited set of actions, which means it cannot do just anything that it wants, but it can only do what the model allows. That combination, start state, actions, and goal, is enough to turn the problem into search. And so the main point here is not robots. The main point is that once you can describe a domain this way, you can use generic search methods to solve it. So now we take this same example and turn it into structure. So each node represents a state, and each arc represents a legal transition from one state to another. Once the problem is in this form, the question becomes, what paths exist from the start to the goal, and what do they cost? And this is also where you start to see why representation matters. A small change in what counts as a state or what transitions are allowed can change the entire shape of the graph and can impact the difficulty of the search. And now this version matters because this is the acyclic version of the state space graph for the delivery robot. And this version matters because cycles can change everything about search behavior. Cycles allow you to revisit states, which means some strategies can loop or waste effort without additional safeguards being put in place. Making the graph acyclic is a modeling move that simplifies the search space and can make certain properties easier to reason about. And so the point here is not that we always can remove cycles in real problems. The point is to notice what the presence of cycles implies in terms of completeness, termination, and efficiency. And now to apply this again to the cybersecurity field, attack paths are graphs, not stories. So in cybersecurity, we often tell attacks as clean narratives or stories after the fact. But the reality is closer to a graph of possibilities. Attack paths emerge from identity relationships, reachability, trust, and policy. When an analyst or a tool evaluates how could this have happened in regards to an incident, that evaluation involves traversing a graph, not reading a script. A key takeaway is that security controls do not just block one step. They change the shape of the reachable space. A single role change or firewall rule can remove entire classes of paths or can accidentally create new ones. Now, the next example we're going to look at is Google Maps. So Google Maps is a familiar example of search with costs. You have a start and a goal, and you want a path that is good by some criterion, usually time. People usually want to get to their destination as fast as possible. And what makes this a helpful analogy is that the state sometimes needs extra context, like direction, because the cost depends on the move you make next. And that is a reminder that state is not always just location. And then in cyber terms, the next best move can depend on context, like privileges, timing, or detection risk. And then another example is shown on this slide. This is meant to illustrate a partial search space for a video game. And so this slide is actually a concrete example of state explosion. So the game state is not just position, it includes fuel and which coins have been collected. Each added feature multiplies the number of possible states. And the important lesson is that search gets hard fast when you add constraints and bookkeeping. And again, applying this to cybersecurity, in cybersecurity, the same thing happens when you add identities, sessions, cloud resources, policy constraints, and time. The space becomes too large to explore naively, which is exactly why strategy and heuristics matter, which we'll be getting into in the next couple of sections. But before we leave section 3.1, we'll look at one more example, and that would be a robot cleaner. Like a robot vacuum cleaner, for example. And this example is small enough that you can reason about it completely, and that is why it's useful. It's a very standard example given in introductory AI courses. With two rooms that can be either clean or dirty, and a robot that can move or clean, so it has two actions. It can suck, as it says on the slide, which means sucking with the vacuum to make the room that the robot is in clean, or it can move. It can move to the other room. So in such a small state space where you just have two rooms that can have one of two states, they can each either be clean or dirty, and you have a robot with two actions that can either move or clean, you can enumerate the possible states and think carefully about actions and goals. So in this example, it reinforces that even simple domains have structure that can be searched systematically. This is also a good place to ask what counts as a goal and whether we care about any solution or just the best solution, because those choices determine what kind of search we want to run. And if you take the APCV 471 course on artificial intelligence, that one gets a lot more into actually programming, doing some Python programming and creating some intelligent agents. And this robot vacuum cleaner is, at least when I teach that class, is one of the examples, I think one of the first examples that I have students code. So if you're interested in continuing your AI studies and want to get into a class that's a little more focused on programming and coding in Python to solve AI problems, then you might want to consider APCV 471. It's a good class. Now, continuing on, we're going to talk about the learning objectives here for section 3.2, the next section. And at this point, we shift from modeling problems to actually solving them. So the goal of this section is not to turn you into someone who memorizes algorithms, but someone who understands behavior. Different search strategies behave differently. And even when applied to the same graph, they can behave very differently. So by the end of this section, you should be able to reason about what depth first and breadth first search will do, what kinds of problems they work well on, and where they break down in terms of time and space. Now, this slide here introduces the core idea behind almost all search algorithms, that of graph searching. We don't explore the whole graph at once. Instead, we maintain a frontier of paths that represent partial progress from the start, and search proceeds incrementally by extending those paths. Every design, also the crucial insight here is that search is not about nodes in isolation, it's about paths. It's always about the paths between the nodes. And finally, every design decision we make about which path to explore next defines the character of the search. So we're going to talk about several different types of searches in this section. But before we get into examples of specific types of searches, we'll continue talking a little more about graph searching in general. So this diagram here, problem solving by graph searching, gives you a mental picture of what search looks like while it's running. So some nodes have already been explored. You see on the left in black the explored nodes. Some are waiting on the frontier, so those are the red nodes that are currently on the frontier, and many are still completely unknown. Those are the unexplored nodes. The algorithm never has a global view of the entire graph. It only knows what it has seen so far. That limitation matters, especially in domains like cybersecurity, where the environment is partially observable rather than fully observable. It's partially observable, and the environment is changing while you search. So search always operates with incomplete information. Now, this is the generic search algorithm written out explicitly in pseudocode, but don't get too hung up on the pseudocode. This isn't specifically a programming class. But what matters here is the structure. And the structure includes basically that you initialize the frontier with the start states, you repeatedly select a path, you check whether it reaches a goal, and then you extend it by exploring its neighbors. This same skeleton, same basic pseudocode or algorithm for search underlies depth first search, breadth first search, and many other strategies. The details about them will differ, but the main underlying algorithm that you see here is the same, and the algorithm itself is fairly simple. However, the consequences of how we choose from the frontier are not so simple, and we'll see that when we look in a little more detail at a couple of specific search strategies. But while we're still talking about the general graph search algorithm, this slide here makes the key point explicit that the only thing that really changes between search strategies is how we select a path from the frontier. That one choice determines whether the algorithm goes deep or wide, whether it uses a lot of memory, and whether it finds good solutions quickly or gets stuck exploring unproductive regions. This is why search strategy is a design decision, not a minor implementation detail. And here we introduce the idea that of optimality criteria. And that's the idea that not all solutions are equally good. Sometimes any path to a goal is acceptable. Other times we care deeply about finding the best path according to some cost measure. Once we assign costs to arcs, then the paths inherit the costs, and we can talk about least cost solutions. So this slide sets up an important theme for later. Optimization is not free. Chasing optimality usually increases computational costs, and deciding when it's worth it is a practical judgment, not a purely theoretical one. Okay, now we're going to start looking at a couple of specific search strategies, the first one being depth-first search. So depth-first search is the first concrete search strategy that we're looking at in this section, and conceptually, it treats the frontier like a stack, if you have familiarity with programming structures. It treats it like a stack. That means it commits to one path and follows it as far as it can before backtracking. This behavior is simple to implement and often feels efficient because the algorithm is always making progress, but that feeling can be misleading. Depth-first search is not trying to be fair or optimal. It's trying to go deep quickly. And this slide connects the depth-first search algorithm to real cybersecurity analyst behavior. In practice, depth-first search shows up when responders chase one alert or hypothesis deeply. They collect memory dumps, reconstruct timelines, and analyze packet captures, all focused on a single narrative. That depth can uncover subtle attack chains, but it also creates tunnel vision. While one path is being explored thoroughly, other correlated signals in the seam may be left untouched. So that would be the analog within cybersecurity for depth-first search would be chasing one particular alert or one hypothesis in depth, and then the risk being a bit of tunnel vision where that's the only path being explored, and you might be missing some other signals that are worthy of being followed up on. So now back to the algorithm itself, the depth-first search. This slide right here is basically the map before we start walking it, before we start following it from node to node. And this is just used to set expectations. Depth-first search is going to pick a branch and commit to traversing down it. With the start node at the top, you can already see the structure of the tree, and you can anticipate what depth-first search will do. It won't sample broadly, it won't compare options, it won't ask whether a goal is nearby. It will go straight down one path until it can't go any farther, and then it'll backtrack. So this slide is here to orient your eyes before we overlay the search order of depth-first search, which is on the next slide. So here, now we layer the depth-first search behavior onto the same structure. The numbering is the key because it shows the actual order nodes are visited. Notice how depth-first search quickly dives deep into one part of the graph while leaving entire neighboring branches untouched. So if you follow the numbers 1, 2, 3, 4, 5, 6, before it hits a leaf and has to backtrack. So it goes up 2 nodes to the last place that it saw another branch, and then it goes down again, 7, 8, 9. And again, it hits a leaf, it goes back up to the last branch, and then it traverses 10, 11, hits another leaf, goes back up, and so on. And if you follow the numbers, you can see how it is always going deep and then backtracking to the most recent branch where it has another path it can explore, and it goes deep on that one, and so on. And so what you want to get out of this is that depth first search can feel fast because it's always producing the next step, but it is also biased by early choices, by the choice of which path you're going to go traverse all the way down. That bias comes from the neighbor ordering and the stack behavior. If you change the order of neighbors, if these different paths were moved around, for example, and you then followed this algorithm, you could change the whole search trajectory. And then here on this same graph, but without the numbering, just with some nodes labeled, the question is asked, which shaded goal will depth first search find first? And this question is not about finding the best goal. Depth first search is not optimizing anything here. It is simply going to find the first goal that lies along the branch it commits to given the neighbor ordering. And that's why depth first search is so sensitive to representation details. 2 people can run depth first search on what looks like the same problem and get different results because the underlying ordering of the nodes, for example, differs. And in cybersecurity terms, this can be the difference between chasing the first convincing indicator you see versus deliberately checking alternatives. So before we go to the next slide, to answer the question about which shaded goal will depth first search find first, is going to be node D, because it's going to traverse all the way down the leftmost path as far as it can. When it hits the leaf, it goes back up 3 nodes to the the most recent branch, place where it branched, and it goes down the other direction and then goes as deep as it can on the path to the left, always taking the path on the left first. And so that would be node D that it would hit first. So now let's talk about the complexity of depth first search. So this slide is where we pull back and talk about trade-offs. Depth first search does not guarantee the path with the fewest arcs, and it can get into trouble on infinite graphs or graphs with cycles unless you add safeguards like visited sets or depth limits. Time complexity is tied to how deep the search goes before it finds a goal, which might be far deeper than necessary. Space complexity is the big advantage. Depth first search stores far less than breadth first search because it mostly tracks the current path plus bookkeeping. The takeaway is simple. Depth first search is cheap on memory, but it is not reliable for finding the best answers, and it can waste time exploring deep, unproductive paths. So now we're going to talk about another search algorithm called breadth first search. And breadth first search takes the opposite stance from depth first search. Instead of committing to one path, it expands the search outward evenly. Conceptually, it treats the frontier as a queue, meaning paths are explored in the order they are discovered. All paths of length 1 are explored between any paths of length 2, and so on. This makes breadth first search systematic and predictable. It also means breadth first search is willing to delay commitment in exchange for broader awareness of the search space. So, applying this to the cybersecurity field, you could say that breadth first search is SOC triage. So, this slide here is to ground the algorithm in real analyst behavior. So, SOC triage works exactly like breadth first search. Analysts look across many alerts, many hosts, many users at a shallow level before deciding where to go deep. EDR detections, authentication anomalies, and network alerts are sampled for patterns rather than exhaustively analyzed one at a time. And the trade-off is clear. Coverage improves, but certainty is delayed. Breadth first search accepts that uncertainty is unavoidable early on in favor of broader coverage. So now, just like we followed the graph for depth first search, we're going to look at the same graph again, but apply breadth first search to it. So this slide, again, the one with no numbers on it yet, it sets the visual baseline for breadth first search. With the start node at the top, you can already see how breadth first search will expand layer by layer. You can see the top node being row 0, for example, and the next 2 nodes under it, row 1, and the 4 nodes under that would be row 2, and so on. So unlike depth first search, there is no single branch that immediately dominates attention. Every neighboring node at the same depth is treated equally. So I use this slide to emphasize that breadth first search is intentionally conservative. It resists the urge to chase any one path until it has surveyed the immediate neighborhood. So now we're going to look at the next slide where the nodes are numbered. So here we see the actual expansion order. So unlike depth first search that went straight down the leftmost path, that's not what breadth first search does. The numbering shows that breadth first search explores all nodes at one depth before moving deeper. And this is why breadth first search is guaranteed to find the shortest path in terms of the number of arcs. It cannot skip over a shallow solution to reach a deeper one. But the cost of this overall fairness is memory. Breadth first search has to keep many paths alive at once, which becomes expensive as the branching factor grows. But you see here, if you look at the numbering, the root is 1, and then the next nodes it explores, 2 and 3, are 1 level below, and then 4, 5, 6, 7 are the next level, 8 through 14 the next level, and so on. That's breadth first search. And so once again, we're shown another graph and asked which shaded goal will breadth first search find first. And so this question again highlights the defining property of breadth first search. Breadth first search will always find the shallowest goal first, regardless of where it sits horizontally in the graph. Unlike depth first search, the answer does not depend on neighbor ordering in the same way. This predictability is one of breadth first search's strengths. In cybersecurity terms, this is why triage workflows, tend to surface the most immediately reachable issues before more complex attack chains. So, to answer the question before moving on, which shaded goal will breadth first search find first? Well, there's no shading at the root or in the first row or the second row, so it then traverses across the third row, and node C is the first shaded node that it will find. And so to wrap up breadth-first search, we'll talk about its complexity. And this slide here makes the cost of the predictability of breadth-first search explicit. So breadth-first search guarantees the path with the fewest arcs, but it pays for that guarantee with space. The frontier can grow very large, especially in graphs with high branching factors. Time complexity also grows quickly because breadth-first search explores many paths that never lead to a goal. The key takeaway is that breadth-first search trades memory and time for completeness and optimality, which is often a reasonable trade early in an investigation, but not sustainable indefinitely. And now we're just briefly going to mention lowest cost first search. So lowest cost first search introduces a new idea that not all paths are equal. Instead of choosing paths based on depth or order of discovery, this strategy chooses the path with the lowest accumulated cost so far. Conceptually, the frontier becomes a priority queue ordered by path costs. So if you've studied programming and data structures, you may have studied the priority queue as a type of data structure, and that's what it's referring to. And this is an important transition point in this lecture because it shows that search strategies can be guided by quantitative judgments. At the same time, it raises a very practical issue. Defining cost is a modeling decision, and different cost definitions lead to very different behavior. So before we move on to the next section, let's just look at a summary of search strategies that we've looked at and talked about so far. So depth-first search is memory efficient, but unreliable for finding good solutions. Breadth-first search is complete and predictable, but expensive in space and time. Lowest cost first search introduces optimization, but depends entirely on how cost is defined. The takeaway is not that one strategy is best, but that each makes different trade-offs. Understanding those trade-offs is more important than memorizing the algorithms themselves, because understanding the trade-offs allows you to choose the best search strategy for a given problem. So now we will discuss the last section that we're going to cover today, which is section 3.3. And this slide here with the learning objectives signals another shift. Up to now, search strategies have been blind to the goal except when they accidentally reach it. In this section, we introduce heuristics, which allow search to use domain knowledge to guide exploration. So the learning objectives here focus on understanding heuristic functions, best for first search, and A-star search. The emphasis is on intuition and behavior, not formal proofs. So now let's talk a bit about heuristic search. Heuristic search is based on a simple but powerful idea. Don't ignore the goal when deciding what to explore next. A heuristic function estimates how close a given state is to a goal. That estimate does not need to be perfect, but it does need to be fast to compute. By using heuristics, search can avoid wasting effort on paths that are unlikely to lead to a good solution. This is where search starts to feel more intelligent, but also more assumption-driven. And now this slide reframes heuristics in explicitly cyber terms. Severity scores, alert confidence levels, and threat intelligence rankings are all heuristic signals. They are not facts, they are judgments encoded as numbers. These signals determine which attack paths get explored first and which ones are ignored. Long before a human analyst makes a conscious decision, heuristics have already shaped the outcome of the search. And this slide grounds heuristics with concrete examples. In physical navigation, distance or travel times make natural heuristics. In more complex problems, heuristics are often derived by solving a simplified version of the original problem. And the key lesson is that heuristics come from abstraction. You deliberately ignore some constraints to get a fast estimate, and that simplification is both the strength and the weakness of heuristic search. And so you can read through these examples given on this slide, which cover points on a Euclidean plane and the cost being the distance. And another example is if the nodes are locations and cost is time, then we can use distance to a goal divided by the maximum speed. And then the next one is if the goal is to collect all of the coins and not run out of fuel, like in that video game example in the last section, then the cost is an estimate of how many steps it will take to collect the rest of the coins, to refuel when necessary, and to return to a goal position. So those are just different ways of calculating cost using different heuristics. So next, we'll talk specifically about heuristic depth-first search. So heuristic depth-first search is a transitional idea that helps you see how heuristics change behavior without changing the underlying go deep attitude of depth-first search. It still commits to one branch and keeps going, but it chooses the next step based on what looks closest to a goal. The key lesson is that adding a heuristic does not automatically fix depth-first search. It still inherits depth-first search's weaknesses, including sensitivity to early choices and the risk of getting stuck exploring an attractive-looking but dead end. And then next, we'll talk about best first search. And best first search is where heuristic guidance becomes the main driver. Instead of committing to depth, the algorithm always chooses the frontier path whose end looks closest to a goal according to the heuristic. This feels more intelligent because it is explicitly goal-directed at every step. The trade-off is that it can be confidently wrong. If the heuristic is biased or inaccurate, best first search can chase the wrong region of the graph very efficiently. And this slide is here to make the heuristic values feel real rather than abstract. So you can visually see why certain nodes get attention first. Their heuristic values make them look promising. This is the moment to in this slide is a good place to emphasize that heuristic search is opinionated. It's not just a simple predetermined algorithm like depth first search or breadth first search, but it's opinionated in the sense that you have to decide what heuristics you're going to use. It's not systematically exploring the spaces like breadth first search. Instead, it is steering towards what the heuristic says is good and towards the quality. And as a result, the quality of the search rises or falls with the quality of that estimate. And then this slide addresses the A star search. So A star combines two forces that we've been treating separately. One is the cost you have already paid to reach the current node. The other is the heuristic estimate of what remains to reach a goal. So A star adds them together into a single priority score. Conceptually, A star is balancing progress so far with expected work remaining. This is why A star is often described as a disciplined compromise between greedy best first search and lowest cost first search. And then here is an example, an acyclic example with heuristics. So this example gives you a clean environment to see A star behavior without the complication of cycles. The value here is clarity. You can track how the algorithm's priorities evolve as it expands the frontier. You will see cases where a node with a great heuristic value is still not chosen immediately because the path cost to get there is already expensive. That tension is the whole point of A star. It is not simply follow the heuristic, but its goal is to minimize estimated total cost. And then here we have the cyclic variation. So this second version is useful because it forces you to rely on the algorithm's decision rule rather than your memory of the first diagram. So, you know, often when you're learning this algorithm, you might think that you understand A star after one walkthrough, but making a small change in the graph exposes, you know, whether you're actually following the logic of the algorithm. So this slide helps reinforce that A star decisions come from the combined score, not from closeness to goal alone, and not from cheapest so far alone. And now this slide shows that A star does not replace the generic search algorithm that you saw earlier. It reuses it. The only difference is how the frontier is ordered. Instead of depth, breadth, or cost alone, A star orders paths by the combined estimate of work already done and work remaining. That continuity matters. It reinforces that many search algorithms are variations on the same underlying skeleton, distinguished primarily by how they prioritize effort. So now we can talk about the complexity of the A star search. This slide is where we step back and talk about realism. A star can guarantee optimal solutions under certain conditions, but those guarantees come at a cost. Time and space requirements can still be very large, especially when the heuristic is weak. If the heuristic provides little guidance, A star degenerates towards uninformed search. And so the important lesson here is that heuristics don't just affect correctness, they affect feasibility. And next we'll talk about the admissibility of A star. So admissibility is actually the formal condition that makes A star special. If the heuristic never overestimates the true remaining cost, then A star will always find an optimal solution if one exists. This slide is about when guarantees apply, not about proofs. So the takeaway is that optimality is conditional. It depends on assumptions about the heuristic and about the problem structure. Those assumptions matter more than just the algorithm name. And this slide is just to make the point that A star is how cyber tools prioritize. So this is where the algorithmic discussion we've been having lands in actual practice as a cybersecurity analyst. Many cybersecurity tools behave like A star, even if they never formally use that name. They balance effort already spent with estimated risk or impact ahead. And so, metrics such as analyst time, response disruption, and business impact function like costs. And the likelihood of compromise and blast radius, they function like heuristics. The key point is that prioritization is not neutral. It encodes values and trade-offs. And now we just talk about how do good heuristics help. So this slide basically asks you to reason about what heuristics actually do. Paths that look promising enough get expanded. Paths that look too costly or too unlikely are ignored. Better heuristics narrow the search space by ruling out bad options earlier. This is not just about speed, it is about focus. Good heuristics concentrate attention where it matters most, while bad heuristics waste effort or create blind spots. And this slide brings us to the end of the lecture. So we've covered different search strategies in sections 3.1, 3.2, and 3.3. And this slide just recaps, again, all of the different strategies that we've discussed. And it ties the week's new content together. And some of the key takeaways are that uninformed strategies trade memory, time, and completeness in different ways. And heuristic strategies introduce judgment and assumptions. A star shows how cost and heuristic estimates can be combined in a disciplined way, but only under specific conditions. And the broader lesson is that search is about managing trade-offs under uncertainty. And this theme will carry directly into next week when we talk about constraints and optimization. So I wish everybody a good week, and reach out to me if you have any questions, and otherwise I will see you next week.